So to prove the right-left direction, assume there are Q1 up to Qn such that Q equals P1 times Q1 plus up to Pn times Qn. Yes, because that's by definition of an ideal generated by P1 up to Pn, and also each each polynomial is in Z, or Z x1 up to xn. Yes, because that's the definition ideal. Since we have Pi equals 0 as assumptions, and 0 plus 0 is the instant of the axiom, and the law 0 times Qi equals 0 is derivable, then it will be we can just do simple induction to prove that we can always find deduction to Q equals 0. And for the left to right direction, notice that the ring axioms and Pi equals 0 are all Horn clauses. And a formula is a Horn clause if it contains at the most one positive atomic formula. So we know all the equality axioms that we put down are all Horn clauses, and the ring axioms are all, the other ring axioms are all Horn clauses, and each Pi equals 0 are obviously a Horn clause. So then we also know from section 3.14 that there is a prologue style deduction of Q equals 0 from ring U P1 equals 0 up to Pn equals 0. So that's the tree style deduction that we see in that chapter. So it then suffices, because we like to have a deduction structure. So what we can do is that we want to show that for each equation s equals t in this proof tree, that s minus t is in IDZ P1 dot 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 Pn. And of course, if this is true for every equation s equals t in the proof tree, then it's going to be true for the equation q equals 0 in the proof tree, and then we're going to end up with q minus 0 equals q in this ideal. And yes, that's awesome. Anyways, so for the baked case, which we do for trees, is when we have a leaf with s equals t. It must be an instance, because it's a leaf, of a ring axiom, reflexivity of equality, or Pi equals 0. If it's an instance of a ring axiom or reflexivity, we have s minus t is equals 0 in IDZ P1 up to Pn. Because, it's a very simple check, just subtract both sides and that equals 0 by applying the typical laws. And we also have, trivially, we also have Pi equals 0, Pi minus 0 equals Pi, and that's trivially in the ideal generated by P1 dot 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 Pn. Just use the one polynomials and zeros everywhere else for the ith polynomial. So the inductive cases for the inner nodes are also very simple. And I don't want to write out every inductive case, but just a simple example from one step is that if the inner node s equals u follows from transitivity of s equals t and t equals u, then by induction hypothesis, s minus t is in IDZ P1 up to Pn, and t minus u is in IDZ P1 up to Pn. By closure of ideals, we can just take the s minus u, and that's really just equal to s minus t plus t minus u. And we know those other two are in ideals, so the sum of it must be in an ideal of the same ideal. So therefore, s minus u is in the ideal of generated by P1 up to Pn by the ring Z. And so by induction, we know that since q is equals 0 in the proof tree, q minus 0 equals q is in the ideal generated by P1 up to Pn under the ring of Z. Oh, by the way, note as a corollary, we have the following theorem. The ring s equals t if and only if s is equivalent to t. So this really just says that the ring proves s equals t if and only if s and t represents the same polynomial. So this just means that everything we're doing just makes sense. And the reason why this is true is very trivial. We just plug in n equals 0 and p equals s minus t in the previous theorem. So this theorem takes the word problem and reduces it to a question of ideal membership. And we have similar theorems for different specific types of rings And it relates to also different types of ideals, which are the easier to work with. And that's what we're going to use the mean result for, and which is the using the Grobner basis to decide decidability of universal formulas. So the proofs are similar, and they can be found in Harrison, is for theorem 5.17, which says for any x, p1x equals 0, pnx equals 0 implies qx equals 0. So the word problem holds in all torsion-free rings if and only if q is in the ring generated by p1 up to pn the set generated by p1 up to pn under the ring q. And it's not z this time. And that's a very important distinction. We also have theorem 5.21, which says that any x, p1x equals 0, up to pnx equals 0, implies qx equals 0, holds in all integral domains of characteristic 0, if and only if there is a non-negative integer k, such that qk is in idq p1 up to pn. And this is a very important theorem, because one of the things that we like to talk about is C, the complex numbers, which is an integral domain of characteristic 0. So why are these word problems ideal? So why do we want to take the word problem and reduce it to or make it equivalent to an ideal membership problem? Why is this important? So it's important because for an arbitrary universal formula, we can subtract it from, we just take an arbitrary universal formula. It's important because we can decide universal statements. And to show this, take an arbitrary universal formula and subtract from both sides of every equation to get 0 on the right. Then by putting the inside formula in canonical normal form, we can distribute the universal quantifier so that each clause is in the form any x1 up to xn, and the conjunction of pxi equals 0 implies disjunction of qx equals 0. And if the clause has no qj, the formula is equivalent to full sum, since the ring axioms in pix equals 0 are definite clauses, and thus cannot be unsatisfiable. If there are exactly one qj, this is just a word problem. If there are several qj, well, we exploit the fact that this theory is defined by that a theory defined by horn clauses are convex, and the proof of this is in Harrison theorem 3.39. And we can rewrite the clause as the disjunction of the conjunction, we can write disjunction of word problems, which is great. So all of these cases, it just dwindles down to a problem of the word problem. So thus we can solve the entire universal theory of rings if we can just solve the word problem. And this is just awesome right here. But then we can also show the word problem's equivalent, but we've already shown the word problem is equivalent to ideal membership problem, which all we have to do is just show that. So how do we solve the ideal membership problem? So one way is to solve the system of linear equations. So for example, to prove x4 plus 1 is in the ideal generated by x squared plus xy plus 1 and y squared minus 2 under the ring Z, well, one thing we can do is we can just guess terms and then solve for coefficients. So let's just guess that the multi-degree, which is the sum of the, that we only need terms of multi-degree less than or equal to 2 in the cofactors, which is just, multi-degree is just the sum of the exponents. So, in a polynomial. So, okay, so x squared plus xy plus 1 has to be multiplied by this term, which has multi-degree at most 2. So x squared has a multi-degree of 2, y squared 2, xy is 2 because each one has exponent 1, and then you have the exponent 1 and 0 cases. And the same thing with the other term being that we're trying to guess, that's the multiplied by y squared minus 2. And that has to equal to x squared plus 1, or x to the 4 plus 1, yes. So when we expand,